All right, so welcome back. This is part two of constraint optimization over here. Constraint optimization. Mm. Um, so hopefully you've watched part one of the constraint optimization. So we're going to continue with that today with kind of practicing what we've learned. So this is Professor Wu, and this is course at Northeastern University. So let's try to do a quick refresher of what we learned last time. In the last class, we basically learned how to solve like basic constraint optimization problems. In this class, we're going to learn to recognize these problems, kind of like do a little practice to convert like real life problems, not real life, but like, actual situations into these constraints. So, to get started, let's start by refreshing what we were doing last time, okay? By practicing solving a constraint optimization problem using the KKT condition. Now, if you remember, the KKT condition have it has four parts: stationarity, primal, dual, and there's this thing called complementary slackness. So see if you can solve this by hand and see if you can solve it by numpy. Okay, you want to minimize x such that you have this. All right. So at this point, pause the video, give it a try. We'll move on. So here's the solution. Given the problem, right, we first convert it into a Lagrangian. So if this is the objective, here's the constraint. So what we did is objective, Lagrange multiplier, and the equality constraint. Remember, we set the equality to 0. Okay. So after we have the Lagrangian, we've used the stationarity condition and the primal feasibility. Essentially, the stationarity condition allows us to set derivative of the Lagrangian to 0. And if we add the primal feasibility, then we end up with a solvable linear system, a b equals to y, basically. And you just solve for b in this particular case. Once you solve it, you can use RREF to solve it. Right? Hopefully, you did the homework, the extra credit homework on RREF, and you'll see that the solution is 5 minus 2.5. Now, this problem, we in the last lecture, I also show you how to solve this by putting the objective in and the equality constraint. And then you call the command minimize with some starting point, and it will automatically find a solution. Notice the solution is equal here. Okay. Now, if you don't remember how to solve this, you might want to review how you will go about solving this through the RREF method. Okay. So this is one way to solve it. Now that we have had some refresher from last class, let's now solve a war problem. So let's say it's year 2030 and the world has ended due to some kind of zombie apocalypse. So somehow you became the leader of a very large group of 100,000 survivors. Now, you are the leader and you want to protect the citizen because there are zombies around. You want to build some kind of protective wall. So you're thinking, why don't we build a rectangular wall around the city, right, that you're constructing? So you want to build a rectangular wall. Okay. Now, ideally, you want to maximize the area so we have some place to live in. While there are some constraints, even though you want to maximize the area. So this is the width times height. You want width times height to be as large as possible, right? But you have some constraints that your army, right, to protect from the zombies, can only realistically guard a perimeter of 20 miles against the zombies. So what should the width and the length, I guess length, be for the city? Okay, to essentially maximize the area. This is a very common constraint optimization type of problem. So at this point, take a moment, see if you can convert this problem into an constraint optimization problem. Okay, all right, pause the video, just think about it for a second. Okay, we're going to move on. So, so well, we know that we're going to let x1, right? We're going to let x1 and x2 be essentially the length and the width of the city, right? So essentially the area would be length times width, right? So you want to the goal here is to maximize the area. So if you want to maximize the area, it's equivalent to minimize the negative area. So we in optimization, normally people like to either pick one, and you always convert the problem into that one. And the one that I feel like is better is minimization. So just always make it into a minimization problem. Now that you have a minimization problem, there's some constraints. It's saying that you can the your army can only guard 20 miles against the zombies. This means that x1, x1, x2, x2. That means 2x1 plus 2x2 has to be well, ideally equal to 20 miles. It should be less than, but since we're trying to maximize, we want it to be equal to. So we want the entire perimeter to be 20 miles because that's the maximum you can do. So therefore, that's the constraint. We want to maximize the area given that your army can only guard 20 miles. Now, guess what? Do you remember the problem we just solved? Right? We're trying to minimize x1, x2, subjected to 2x1, 2x2 equals 20. That's literally the problem we solved in the beginning, right? Minimize the negative area subjected to the perimeter is 20. Like exact same problem. So we just did it. So this is this we now see that the constrained optimization problem in action. Essentially, how we converted a word problem, like a potential situation, into constraint optimization, and you should know how to solve it. Okay. Now let's try solving this. So your army can only guard 20 miles. Moreover, you want to build one side between two mountains of 3 miles apart. So let's say you have this, right? This is this two mountains. You want to build it here. Therefore, this is only 3 miles apart, implying that one side of the rectangle cannot be. So what this is saying is that you have a constraint. You have a constraint that you want x1, right? This is x1, x1, x2, x2. X1 has to be less than or equal to 3. All right. So everything the same from the previous question, and then we added this extra constraint where one side cannot be greater than 3. And therefore what is the x1 what is x1, x2, right, to maximize the area. So take a second and see if you can solve this. Pause the video and go ahead. This should not be a difficult problem. Okay, now I didn't provide the answer for this. So you want to like pose add this extra constraint. Make sure you check whether this constraint is active or not, right? And remember what active constraint means. And once you realize it's active or not, then the rest of the problem should be very easy. And make sure you ask your neighbor, ask another person doing this problem to see what they got. Okay. All right. Next problem. So remember that you remember the teaching from Professor Wu that and realize that building a circle instead of a square will maximize the area. So ideally, you don't want a rectangle, you want a circle. All right. So let's look at the math. So in the last example, we realized that x1, x2 would have been 5 mile by 5 mile, right? So that would have been 5 by 5. If you have 5 by 5, then the area was 25 square mile. So 25 square mile that came from the rectangle, right? and with a perimeter of 20 miles, right? So about 20 miles. Now, given a circle, let's say we have a circle, and the equation for the perimeter is this, right? And therefore, the radius of a 20-mile circle, right? If we know that the radius, instead of rectangle, we have a circle, and if the radius 20 miles, it means that the radius is roughly 3.18. Okay? So if we have 3.18 as the radius, what is the area? Area is radius squared times pi. All right. So if you have radius squared times pi, then the total area is 31. Now remember, had you build a rectangular wall, which would have been 5 by 5 mile, then you would have had 25 miles square. But if you use a circle instead of a rectangle, you would have 31 miles, 0.83. So 31 versus 25, like that's much larger. You can see that by building a circular wall as opposed to rectangular wall, you essentially maximize the area while minimize the perimeter. So you need to guard the least amount of perimeter while maximizing the area for people to live in. Okay. Well, so now let's say you did this, right? You end up building a circle because you remember Professor Wu's class, and now that you remember, when we finish building the circle, there's another colony. So we're the Northeastern University colony, and there's an MIT colony. The BU colony was destroyed. BU was destroyed. So we used to be friends. No, actually, we were never friends. But anyway, so the BU colony was destroyed. Actually, BU is here. BU is here. They were destroyed, and therefore, in Northeastern, we basically hold most of the refugees from the BU colony. But anyways, we trade. Our biggest trading partner is the MIT colony, and the location where we trade is we decide to pick the midpoint, which is this point. So here's the Charles River, and over here is the end of the bridge. Well, we picked that as essentially the midpoint between us, roughly, so that we have basically the same danger. So you have to travel the same amount through the zombies, and so do they. So therefore, we are facing equal amount of danger. So the point is, well, ideally, we want to put a door here because we trade with them the most. So if we build a circle where this location is 0, 0, right, center of the circle, where should the door be such that it minimizes this distance? Okay. So you need to find, like, as a leader, and you need to decide where is the door. You need to figure out this exact location of the star so that the distance to here is minimized. So that's the second word problem, right? So to trade, we meet the MIT colony at the Harvard Bridge and Mass Ave, so the corner here. And given the center of our city, we're going to call that 0, 0. And we know that in relation to the center of our city, this location, the trading post at the bridge, is 4, 6. Okay. So if we know this point, right, which is 4, 6, and we know the center of our city, and we know the radius as well, which is 3.18. 3.18. So we need to know essentially where this point is. Okay? By knowing this point, we can allows us to build a door that's closest to our trading point. Imagine if you messed up really badly, you decide to build a door here. Now you have to walk really really far, right? That would suck. Or imagine if you build a door here, so you have to travel all the way around. So a lot of people could die from the zombies all around us. So by picking where the door should be, I mean, obviously we'll probably have multiple doors, but where should this door be for the trading purpose? It will minimize the distance which you have to travel, and lowers the chance you'll get attacked by zombies. Okay. So that's the second world problem. See if you can identify the equation and see if you can like solve the problem. Okay. So that's part two. Like write out the constraint optimization and see if you can solve it. All right. Pause the video. Take a second. Think about it. Remember what the equation of a circle is. Okay. Equation of a circle is, um, I think it's x squared plus y squared, something like that. Is that right? Oh yeah, minus the center. Minus the center. Yeah, x1, x2 minus the center. x1, x2, x1 minus the center plus x2 minus the center square. Anyways, so refresh yourself with the equation of a circle. That will be necessary. Okay, so um, hopefully you took some time to think about this problem. So given x1, x2, so let's say x1, x2 is the point. So we want to find x1, x2 along the along the circular wall. So then the distance between the door and MIT. Oh, I see. That was the distance. What was the equation of a circle? Oh, it was this. So I was right. That's the equation of a circle. So, anyways, so the distance between, okay, so if we know this point and we know this point is 4 6, then the distance between them is x1 minus 4, x2 minus 6, and square of that. So this is how you find it. This is the equation of a distance essentially. So if you know this is the equation of the distance, and therefore we want to essentially find x1 and x2 that minimize this distance. However, this x1 and x2 can't be any point. It has to be along a circle. Okay. So now that we know the radius is approximately 3.18, therefore the equation that describes the circle is this, right? It's x1 squared plus x2 squared is equal to the radius square. So this right here is saying that, well, we know the radius. Therefore, it whatever x1, x2 you get, it must satisfy its constraint, because the constraint is that the wall, the door is along the circle, right? So whatever x1, x2 point you pick, the the radius the radius must be 3.18. Okay, so that's the idea. So now we have a constraint, right? We have the minimization problem. We have a constraint. Now, when you're trying to minimize something, you can also do the square to get rid of the square root, because minimizing something versus minimizing something square is the same. So that will simplify. Now, if you just go ahead and solve this, like you might need to solve this with Python. So the final result is you should get 1.76 and 2.64. That is the location. Okay, so that's how you go about solving this. And I think this problem you probably can't solve it by hand. You would need to solve with the Python. Okay, so let's see, 1.76. So this is the code I wrote to solve this, and it says that the location is 1.76, which is right 1.76 is right around here. See, that's where the door should be, and what 2.64, 2.64. Let's see, 2.64. So somewhere here. So that it's see. Notice how we're able to find the exact location of the door, right? And here's the code. We've done this code multiple times by now, so I'm not going to go over the code. So notice how the code allows us to find the location of the door. So this is the city center. This right here is the Harvard Bridge. Right, this is our trading post. And this area is the danger zone. You could get killed by a zombie anywhere along this line. But this is how you minimize the distance. Okay. All right. So I guess that is it. That's it for this part of the lecture. The next part, we're going to go over the concept of duality. And yeah, that's it. I will see you in the next lecture.